Welcome. This question says a 70 kilogram mass is located at 2I plus 3J plus 1K meters. What is the gravitational potential energy for a 5 kilogram mass, which is located at 3I plus 2J plus 4K meters? So this is, again, it's a gravitational potential energy question, but whereas before we tended to put the host mass, the heavier mass at the origin, now we're moving to a more general case. And our host mass, our big mass, is here, 70. And this is at 2I plus 3J plus 1K displacement from the origin. I know where it is. And then the mass of interest, a 5 kilogram mass, is at another point. I'm not trying to draw these with any kind of anything other than symbolically, schematically. I have no idea what arrow to draw for this. I'm just drawing an arrow, but it's helping me visualize. And this would be 3I plus 2J plus 4K meters. And what I want to visualize is the separation that I'm looking for. If I look at this, I'm being asked, what is the gravitational potential energy of this 5 kilogram mass? And so the expression, the equation I want to use is UG is equal to minus M1, M2, there's your two masses, over R. And R in this case is a separation. And where is that separation? That separation is here. If you like, it's the magnitude of the vector which goes from the 70 to the 5. I want the magnitude of that red vector. But I don't have it. In fact, I don't even have the vector pointing, the displacement vector pointing from the 70 to the 5, although that would be a good first step. If I think back about my vector diagrams, if I think of this vector here between the 70 and the 5 has been a resultant, then I could get that vector by having the vector from the 70 back to the origin as a first step, and then having the vector from the origin to the 5 as a second step. Remember what we do with vector diagrams. We say, well, the resultant is equal to other vectors added together, and the way you add them is you put the tail of the second vector on top of the head of the first vector. So that red vector, the displacement of the 5 from the 70 kilogram, is equal to this first green vector added to the second green vector. And I can figure that out actually. I can do a table I, J, K. I'll leave this all in green so that we know it's all about this diagram. And for the first step, I don't want from the origin to the 70 kilogram, which is what the blue vector is. I want from the 70 back to the origin, which is what the green vector is. So rather than having plus 2, I would have minus 2. And rather than having plus 3, I'd have minus 3. And rather than having plus 4, I'd have plus 1, I'd have minus 1. So my vector displacement from the 70 back to the origin would be minus 2I, minus 3J, minus 1K. And then the second step would be going from the origin to the 5 kilogram mass. And it turns out that's what the question gave me. So that would simply be, oh, I already know this. This is 3I plus 2J plus 4K. So I need to add these things up because that's how you do vector addition. You add the two vectors up. So this would be plus 1i, that would be minus 1j, and it would be plus 3k. So there's my vector, the red vector. Maybe I should write it in red. Plus 1i minus 1j plus 3k meters. Okay, well, at least I know the vector pointing from the 70 to the 5. But what I really want for this equation is the actual magnitude of that vector. I want the physical distance. That's not hard at all. I just simply say use Pythagoras in 3 dimensions. So it's going to be plus 1 all squared added to minus 1 all squared added to plus 3 all squared, and find the square root of all that, which is the square root of 11, 1 plus 1 plus 9, square root of 11 meters. Well, if I transfer that back up to here, I can say that UG is equal to, oh my word, I don't believe I forgot that. G, of course, has to be in there. UG is equal to minus G. It's going to be 70 times 5 over the square root of 11. So UG is equal to minus G 350 over the square root of 11. I like to do as much on the paper as little in my head as I can do. So that would be 350 divided by second square root 11. So that would be 105.5, call it 106. So UG is equal to minus 106 G. That's the numerical value, even though I've not actually worked out what G is. And that is going to be, of course, in joules. So there's my answer. And if I look on here, yeah, minus 106 G joules. It's there. So if we compare this with some other examples where we have to work out the gravitational potential energy at a given point, in the end it comes down to this equation, but I added complexity here by not giving you this separation value, or not giving you a vector from which you could easily work out the separation value. In this case, I made you work a little bit harder. You had to visualize the two vectors. You had to recognize and draw in the vector that was associated with the separation that you wanted to find out. And then you had to do, it's very reminiscent of the, you had to basically use IJK vector manipulation to work out the vector that you wanted, so that you could then find the magnitude of that vector, which is the separation. So the complexity here is really as far as the visualization and the vector manipulation is concerned, laid on top of just knowing your basic equations for, in this case, for the gravitational potential energy of a mass at a given point. So there we have it.